the cross product is defined only in 3 dimensions. So, in a 3-dimensional XYZ coordinate system, and we still have our I and J vectors, unit vectors in the directions of the X and Y axes, and now we have a K vector, a unit vector in the direction of the positive Z axis. Now we define the cross product without motivating it. Let's just define it and see how it works. Okay, the right-hand rule applies when we do what's called a cross product, and we define the cross products of I and J, I and K, J and K in terms of the right-hand rule. Now the right-hand rule says, let's say we want to find the cross product of the vector I and J. Okay, the vector I goes in this direction, and the vector J is over here. So if we want to turn our fingers from the direction of I toward the direction of J, we're going to have our hand in this position. If our hand was in this position, we could turn the I vector toward the K vector, but we wouldn't be able to turn the I vector toward the J vector. Now, if our hand is in a position where we can turn the I vector toward the J vector, our thumb points in the direction of the positive Z axis, that is, in the direction of the K vector. So by the right-hand rule, we define I cross J to be the K vector. We define I cross K to be the negative of the J vector, because if our fingers point in the direction of I and our hand is oriented so that we can curl the I vector toward the K vector, our thumb points in the direction of the negative J vector. Similarly, J cross K. Okay, J is here. We turn toward the K vector, our thumb points in the positive X direction, in the direction of the I vector. We also define I cross I to be 0, J cross J to be 0, K cross K to be the 0 vector. These are not 0, they're the 0 vector. That's why they have arrows over them. Okay. And also a rule that if we reverse the order of the cross product, we get a negative. We don't really need that rule. If we do, for example, J cross K is I. If we do K cross J, we have to have our fingers in the direction of K, curl toward J, and our thumb points in the negative X direction. So the result would be negative I. And if you do K cross I and J cross I, you'll find that we get the negatives of these results. In any case, we'll state that as a rule, but that's also a result of the right-hand rule. Now, why do unit vectors crossed with unit vectors give us unit vectors? There's a motivation for that, but let's just see what the consequences of these definitions would be, or of this definition would be. Now, we're going to say that most of the rules of algebra apply to calculation of cross products, but of course, as we've just seen, the cross product isn't commutative. I cross J is the negative of J cross I, so I cross J is not equal to J cross I. Okay, well, we're going to do an example where we find the cross product of the vector 2i plus 3j with the vector negative 2j plus 5k. Sketch these vectors in the coordinate system, and 2i is here, 3j would be over here. Add them together, we get a vector that originates here, terminates here. And similarly, negative 2j is here, 5k is here, so negative 2j plus 5k is here. We do the cross product using distributive law. So most of the rules of algebra apply. Distributive law is one of them. 2i times negative 2j. 2i times 5k. You should write these out before you read what I've got here. But then 3j by 2k, 3j by 5k, 3j times negative 2k here, and times 5j. Well, associative laws work, so we can bring our scalars together. 2 times negative 2 is negative 4. 2 times 5 is 10. 3 times negative 2 is negative 6. And 3 times 5 is 15. And there's something wrong there. Hang on. Never mind. There's nothing wrong. Okay. And then, of course, on this product, we've got I cross J. Over here, we've got I cross K. Over here, we got J cross J. And over here, we got J cross K. Now, we can check, or we can just use the right-hand rule. We don't really, once we understand what the right-hand rule says, we don't really need to refer to this list. I cross J is, well, I's here, J's over here, that's K. Now we have a negative here, so we have negative 4K. And then I cross K is negative J. J cross J is 0, and J, and that should actually be the 0 vector. Anyhow, J cross K is, here's J, here's K, that's I. So we've replaced those quantities here, except that I should have had an arrow over this vector, because we're adding vectors. Okay, well, when we add these things together, what do we have? We've got I cross J being K, we have negative 4K, negative 10J, and 15I, and we don't have to write a multiple of the 0 vector. Putting those in the order I component, J component, K component, we get 15I minus 10J minus 4K, which is the vector. Also, we could write in it as an order triple 15, negative 10, negative 4. Now, I observe that if I do the dot product of this vector with this vector, and of course this vector is this one, and I've got the 0K in there. It wasn't necessary to write the 0K here, it wasn't necessary to write the 0I here, but if we want to do the dot product, we're going to have I, J, and K components, and the dot product here works just like it does in 2 dimensions. We multiply the I components, 15 times 2, J components, negative 10 times 3, K components, negative 4 times 0. We had to write the 0K here, so we'd have something to multiply by the K component here. And then we add those up. Clearly we get 0. And as before, the dot product is a product of the magnitudes times the cosine of the angle. If the dot product is 0, that means the cosine of the angle between the vectors is 0, meaning the vectors are at 90 degrees. So the cross product here is at 90 degrees with both of these vectors. Now, it may be a little hard to visualize that in space, but you can try. Just think of a pane of glass across these vectors. It'll point sort of back in this direction and down below the XY plane. A little bit more about that direction a little bit later. We're not going to get too heavily into the equations of planes and so forth in this course. But the direction of this cross product is an important quantity. Now, more generally, if 2 vectors can generally be expressed as so. Let's call this the A vector, let's call this the B vector. Any vector that we want to call the A vector is going to have I, J, and K components that we can call A sub X, A sub Y, and A sub Z. Any vector at all can be expressed in this form, and any vector at all can be expressed in this form, so that we have a general vector multiplied by a general vector. And when we do this, we again use the distributive law. AXI times each of these components. So we have AXI here, AXI here, AXI here, and our components of the B vector in order here. And similarly with the other rows here. We have AY in all of these, then BX, BY, BZ, AZ in all of these, and BX, BY, BZ, and we have the right unit vector on each. And we want to have our bookkeeping. You know, we have IJK, 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 I's here, J's here, K's here. When we simplify this, I've written the intermediate step here where I've just brought in this case, the AX and the BX together here with the I cross I over here. Done the similar thing everywhere else, and I get this product. I observe that I cross I, J cross J, K cross K are all 0. And then I work out. I cross J is K. I cross K is negative J. J cross I is negative K. J cross, well, we did that. J cross K is I. And K cross I being J. K cross J being negative I. Here's our product. And then we can do some grouping. We want to group these as to I, J, and K components, and that's easily done. We have I components, A, Y, B, Z, and negative A, Z, B, Y. So right there's what we get for the I component. And grouping similarly, we get the J and the K component. Now there's a pattern here. This is I, which corresponds to the X, and there are no X components here. And that's because the AX, BX, the X components do what they do, giving us zeros here, here, and here. I'm not going to draw that conclusion in detail, just because of time. You can see if you look and see why that is. But there's no X component on the I's, there's no Y component on the J's, there's no Z component on the components of K. Also, we have AY, BZ, AZ, BY. There's a symmetry here. We have YZ here, then we have ZY here. We have ZX here, XZ here, XY here, YX here. Simple pattern, and easy to remember. If you think that we're not going to use X on the I component, we're not going to use Y on the J component, we're not going to use Z on the K component, so that it's got to be either AY and BZ or AZ and BY. Which one is which? Well, if I write X, Y, Z, and then write another X here, the YZ is like this. So it's the Y, then the Z. The ZY is like this, Z, then Y. Goes backwards along this cycle. The first one goes forwards along the cycle. So that if it's X and Z, which goes first? Z precedes X. And then, of course, X precedes Z in the opposite direction. So if you see that pattern, it makes it sort of easy to remember. Much easier anyway. Now, it's not absolutely necessary to memorize this pattern or understand it, although it's desirable. The more common way of writing this is the determinant of the matrix that has I, J, and K for the first row, the AX, AY, and AZ components of the first vector for the second row, and BX, BY, BZ components of the third vector for the third row. The determinant of this, if it's expanded in minors, and I assume we know that at this point, how to do that at this point, is going to be I times this minor, I times the determinant of, well, I've written it down, I'm not going to read it to you. Just in the interest of time, don't want to take up much of your time here. Okay, and then we have minus J times the determinant of the minor that we get when we eliminate this column, the AX, BX, AZ, BZ column, and similarly for the K. And you can verify, since you know how to do determinant of a 2 by 2 matrix, this diagonal minus this diagonal, that you do get this expression out of that. We can easily prove that the cross product is perpendicular to the second vector, and we could do the same with the first vector. We just take the dot product of the second vector in this case with the cross product that we calculated over here. We use the distributive law and so forth, and we quickly see that this term matches this term, except this one's negative. This term and this term match, but this one's negative. This term and this term match, but this one's negative, so we get 0. Now that tells us that A cross B is perpendicular to B. And we can similarly prove that A cross B is perpendicular to A. Now it'd be really messy to write it out, but we could easily prove this if we can just keep track of all our terms. So that the cross product has the characteristics that it's perpendicular to both of the vectors, and it has magnitude equal to the product of the magnitudes times the sine of the angle between the vectors. These conditions could be taken as the definition of the cross product, as could the determinant formula or the formula that we derived previously. All three potential definitions completely equivalent to our definition.